and how they could self-assemble into a variety of structures. These structures included micelles, bilayers, and other more interesting phases. So again, today we're going to spend some time discussing membranes, and today we'll try and finish up with membranes in this discussion. The next thing that we did was to look at something called a sort of shape function or a shape index, and that was something that looked like A naught L divided by, I think I called it nu. So this is the length of the hydrocarbon shales, and the nu was the other way around. I had nu of Hc on top A naught times LCc here. So here we're looking at molecules that look a little bit like this. So nu Hc measures the volume of these chains, so that is this term here. A naught measures the area of the head group here, and LCc measures the height in some suitable unit. LHC, sorry. LHC measures the height of the hydrocarbon chains. And then we said, as we vary this particular parameter, nu Hc over A naught LHC, we found that in different regimes, depending upon nu Hc by A naught LHC, I could get the distinction between micelles, bilayers, etc. And all of this really derived from the shape of the molecule. So the shape of the molecule dictated the packing of the molecule, and packing dictated these large scale structures. The next step, what we need to do is to discuss a little bit about the elasticity of the membrane. So imagine that we have a membrane of, say, some area A0, and now we stretch it. This is a flat membrane which we now pull at from these different regions. We can pull it here, 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 and here until the membrane area increases to an area called A. So the change in the area, delta A, is just A minus A naught. So we can define an energy for stretching, which we call E stretch, which is equal to 1/2 times a modulus, which I will call K stretch, the stretching modulus, times the quantity A minus A naught squared divided by A naught. Okay? So now this is saying that the energy, stretching energy, is minimum when A equal to A naught. So if I plotted this as a function of A and I had A naught here, then E stretch was smallest at A equal to A naught and increased quadratically as you moved away from that. Okay. And this quantity here is called the stretching modulus. From here we can ask, what is the force that I must exert to keep it here and not here? This is now a force per unit area, or lateral stress, and that quantity is, I could call it sigma, which is delta E stretch over delta of A minus A naught, just delta of A, which is the same thing. And that quantity is just K stretch into A minus A naught divided by A naught. It's just a derivative of this with respect to A. I can either take the derivative with respect to A, or I can take the derivative with respect to A minus A naught. These are the same thing, because A naught is a constant. Okay. So this is K stretch times A minus A naught by A naught, which is, I can write this as K stretch times U where U is this particular quantity. A over A naught minus 1. So U measures the deformation or the fractional deformation of the area. Okay. This is really saying nothing much except for the fact that the stress, which is the force per unit area exerted here, this is actually the force per unit length, which is the energy per unit area. The stress is proportional to the strain, which is this term here, the U term here. And what comes inside here is an elastic constant. And we will come back to this particular definition. So this is one way to think about membrane elasticity, or the first important part of thinking about membrane elasticity, which is to look at the stretching of the membrane, and this, which is parameterized by a stretch modulus or a stretch elastic constant. The other thing that we can do with the membrane is to bend it. So imagine that we have a perfectly flat piece of membrane, and we want to take it and we want to bend it over like this. And then let us ask what happens in that case. So here we have a membrane that looked like this, and what we want to do is to make it look like this. Okay. Note that the following things happen here. First of all, there are some lines here that remain the same length. For example, this is a medial line here. Everything above that line is pulled apart. Everything below that line is compressed. So the energy cost for bending this object here comes from the fact that some parts of it are pulled apart, some parts of it are pushed together. It's only on this line here, the elements on this line are neither pushed apart or pulled together, they remain the same. Okay? So this is called, because this is a membrane, it's a sheet, so it's actually a sheet that goes all the way into this. It's a sheet of some finite thickness here, which I call, with that thickness I will call D. And this line here is called neutral surface. And across the neutral surface, there is no stretching, no compression, and no pulling apart. Okay? So now we want to ask what is the energy for this particular bending that we have done here. And for that, we can have an additional modulus here, which I will call E of E bending. And E bending just measures how much the volume change actually is. So this is 1/2 times our old friend the Young's modulus times V minus V naught squared divided by V naught. The Y is the Young's modulus. Remember, we introduced the Y a little earlier in a different context. We said imagine that this has some length L, and now it becomes L plus delta L. And we asked what is the force per unit area required to keep it like that. And we found that the force per unit area was the Young's modulus times delta L divided by L. This really says the same thing, except that it takes it into account a little bit of the fact that we can, over here I sort of assumed that the volume of this chunk remained the same. That when I pulled at it, the two other directions compressed a little bit so as to keep the overall volume the same. In general, they need not do that. And the amount to which they do not do that is measured by something called a Poisson ratio. You can have funny materials where if you pull at them, they actually expand outward rather than contracting. Materials that would pull, if you pull like this, contract to keep the volume the same, are in a sense normal. They're well behaved. And any material which does the other thing, which when you pull it, it tries to expand, that is abnormal or unusual or anomalous in some way. And exactly how that happens is measured by something called the Poisson ratio, which we won't talk about at this moment. But this really is the same thing as here if you just put everything back in and convert the energy to a force, which is what we did here by taking a derivative. And the logic is really the same. The energy is minimized when V equal to V naught. If I want to increase the volume or decrease the volume, I have to pay some energy. I have to apply a certain force to the system. the force that I apply here is equal to the derivative. Just remember, just go back, whenever you're confused, just go back to the energy of the spring being 1/2 k times x squared, where x is the deformation. So the force required to induce a certain deformation x is just delta E of the spring by delta x, which is k times x. So if I take a spring here and I pull it out to an amount x from its equilibrium position, the spring exerts a backward force minus Fx, which I must counter by exerting exactly the same force outward. So the force that I must exert on the spring to maintain a fixed extension x is just k times x. And that's the same logic that goes into taking a force, an energy from here and converting it into a force per unit area of this form. It's just that when I write this only in terms of delta L by L, there is a certain additional approximation that the system volume remains the same. Is that clear? All right. So now let us calculate the bending energy. So as I said, when I take this and I deform it, I have increased the density a bit here, I have decreased the density a little bit here. It's only along the neutral surface that nothing changes, nothing is pulled or pushed apart. So understanding how much energy it costs to bend into this, I must actually calculate how much it costs to change the volume in these different regions and add that up. Okay? So that's what we're going to do. We're first going to write this quantity E bend as E bending, the total bending energy, divided by L squared. And here, L, let us say that this dimension here is h, between here and here, and the dimensions in the other xy direction, this has dimension L. Okay, so that nothing, there's no deformation in that direction. I've just taken, so I've just imagined that this thing goes on in this particular way, and this distinction here, this length here is L, and this transverse length here is L. So both along the xy plane it's L. Okay. So this quantity I will now write as 1 over L squared, an integral between 0 to L, this is the dx integral, an integral between 0 to L, this is the dy integral, and an integral between minus d over 2 and plus d over 2. And over here I must put my little element here. So I'll just write it down and then we can look at it. This is y divided by 2. This is 1 plus z divided by r. So r is the radius of the circle. So if I just imagine that I've fitted this part to a circle, this is the radius of the circle r, and the expression that I will have is 1 plus dz divided by r times dx dy dz minus dx dy dz divided by, so this is whole thing squared, divided by dx dy dz. So these are the little volumes here. I'm imagining that each one of these has a little volume. dx dy dz is a volume when it was not deformed. So it is just a little block like this. Once I deform it, it deforms in the z direction but remains the same in the x and y directions here. How much does it deform in the z direction? Well, that depends on what my z is. If z is positive, then it gets pulled out, the volume increases. If z is negative, it gets pushed in, the volume decreases, and this is the way. We can work this out later, but just sort of take it for the moment that this is how it is. So the d's here come from dx dy dz here. Then which d? That comes from minus d by 2 and plus d by 2. So that is the dz integral. So this is the integral for the z, this is the integral for the, let's say, the y, and this is the integral for the x. Oh, did I call it h? Sorry. I should call it h, sorry. My apologies. H divided by 2. Clear?
So, other y no, inside the integral first term?
1 plus z divided by r. This is y. This is the Young's modulus y. So I'm just taking this particular form here exactly. So y by 2 is a term that enters here. 1 by L squared by definition. And then instead of v minus v0, I'm writing as integral dv dx dy dz for the v and the v0 part separately. And this is v minus v0 squared. So a little element is this, the x and y element, and this is how much the z element changes. So it's just written out in that form so as to make sense. Okay, so now we can expand this. The first term, of course, goes away. That's just dx dy dz and minus dx dy dz. What is left is a z over r times this whole square. This is z squared over r squared, and these terms cancel from the top and the bottom. Okay, so this I will write as 1 over L squared, integral from 0 to L, integral from 0 to L, integral from minus h divided by 2 to h divided by 2, dx, dy, dz, z divided by r, the whole squared, and a factor of y divided by 2.
How do we get like 1 plus z by r?
So 1 plus z by r is, if I take something that looks like this, and then I deform it to look like this. So now I have expanded it a little bit at the top, and I have contracted it a little bit. The amount by which I have done that depends upon how far away this midline is, which is r here from this origin. Okay. So now you can ask what happens to these points. Where does a point here move? The answer is it moves a little bit in this direction, and a point here moves a little bit in this direction. So that's where the 1 plus z by r, just work it out. It's not hard to figure out where that comes from. It's just that it's deformed only in one direction, which is the z direction. X and y remain the same. And depending upon whether you're above this middle line or below this middle line, you have a slightly larger volume or a slightly smaller volume. All right, so now we can, so this dx and the integral dx, integral dy gives me the factor of L squared. So y divided by 2, 1 over L squared times the factor of L squared, integral minus h by 2 and plus h by 2, z squared dz, and I have a factor of r squared here. And this becomes, get rid of these factors here, y divided by 2, 1 over r squared, z cubed divided by 3, between minus h by 2 and plus h by 2. Okay. Which is y divided by a factor of 24, h cubed divided by r squared. Okay, I can simplify this. Okay, so first of all, notice that this depends, as this is proportional to h cubed, which means that it's quite sensitively proportional to the thickness of the membrane. H is the thickness of the membrane because it went from minus h by 2 to plus h by 2. So the thinner I make the membrane, the larger or the smaller the energy and the easier it is to make it fluctuate. So that's the important point about this. So thinner the membrane, the smaller the energy. Which means that if I put it in a thermal environment, the fluctuation should be larger, or larger the fluctuation. So if I define this 2D stretching modulus as K stretch is y divided by h, then the bending energy, E bend, is just 1 over 24 times k stretch into h divided by r, the whole squared. So just relabeling quantities in terms of other things here. So if I define kappa, okay, I will probably use kappa later, so let me just not deal with that for the moment. So just notice that if I have two sheets here, I didn't really worry about the fact that I was always bending a bilayer. So if I have one bilayer at the top and one bilayer at the bottom, I'm bending both of them. The same sorts of arguments apply. It's just that the energy becomes twice this energy. Okay? Because again, I'm taking a sheet and I'm bending it here. So there are certain approximations that go into that. These sheets don't interact with each other, and I can just add up the energy of them separately, bending them separately. But if I do that, then this number just becomes doubled. And sometimes you have to worry a little bit about that when you decide what you calculate. You may calculate things for a single monolayer, but in order to translate it into a bilayer, you need to worry about those factors of 2 and what counts. Okay. So now we having now discussed the bending of the membrane, we are now in a position to discuss other quantities associated with the membrane. Yeah, just a sec. Associated, for example, with the membrane curvature. Yeah.
Use the event in the equation h square by r whole square.
Yeah, so because I pulled out a factor of h here. So I said I define a quantity which is y divided by h. Okay, so to be consistent, I need to define yeah, good point. If I need to write it like this, I have to write y into h. Sorry, it's a good point, because then I combine this, and then I write h by r the whole square. Then it makes sense. Thanks. So remember how we thought of the membrane? We said, here is a membrane. It's a surface in 3 dimensions, which means if it's a surface, I need 2 numbers to specify it. Okay? We said, all right, let us say we specify our membrane by specifying a vector r as a function of those 2 quantities, which I called u and v. And the u and v, remember, we specified in many ways. We said, let us suppose that x is u and y is v. Then r is just the vector x, y, and the height to the membrane above the xy plane, which is hxy. This is one way of doing it. The other way of doing it is to imagine a funny coordinate system where I might use theta, phi to describe where a vector is on this, and say specifying the radius from the origin as a function of theta and phi specifies this closed surface. So if I want to discuss closed surfaces, this might be a more useful parameterization. If I want to discuss flat surfaces, this might be a more useful parameterization. Then we define vectors called T, we call it T or R? We call it R. R sub u, which is delta R by delta u, and R sub v, which is delta R by delta v. Okay, these were what I called tangent vectors, because at any point on the membrane, these vectors are tangential to that point. Then we said, okay, if we take these 2 tangent vectors in the plane, take Ru, cross it with Rv, this is a vector that is normal to both u and v. So if I take this and divide by the modulus of Ru cross Rv, what I will get is a normal vector at a particular point u and v. So this is a normal vector at the point u comma v. Then we said take the membrane and ask what is the distance between 2 points separated by some distance ds. So here is my coordinate system. This is r of u v and this is r of u plus du small and v plus dv. And I wanted to ask what is the distance between this. Okay. So then we expanded that and we found that ds squared was just mod of dr squared, which I could write as Ru du plus Rv dv mod squared, which was something that looked like E times du squared plus twice f times du dv plus g times dv squared. Okay. So this is very important because it tells you how do you understand distances within the surface, which you parameterize by coordinates, internal coordinates u and v, in terms of actual physical distances between points. So this quantity is particularly important for that reason, and there is one measure called the metric, which is what relates distances along the surface in terms of small changes in u and v. And Eg minus f squared is a quantity called a metric. And this quantity is also the same as Ru cross Rv squared, which always is greater than 0. So Eg minus f squared is Ru cross Rv squared. And if I ask what is the infinitesimal element dA, so here on the surface I have vector Ru, vector Rv. So the little region inside here, which has an area of dA, is given by square root of g. So this quantity is called g, square root of g times du times dv. So this is how I write a little element, a little area element on my surface in terms of what I know, which is how the surface is specified in terms of u and v. Let's just do an example. So in that example is the example of Ru. First of all, the case where the surface is specified by specifying the vector r, which is x, y, and h of x comma y. If you remember, I call this the Monge gauge. And now I can do everything here in this gauge, or in this way of parameterizing the surface in terms of x and y, and the height of the surface above the xy plane. Okay? So first of all, what is r sub u? Here now remember, u is the same as x and v is the same as y. So r sub u is r sub x, which is, take a derivative here. So take a derivative of x with respect to x, this becomes a 1. Take a derivative of y with respect to x, this becomes a 0. And this term becomes h sub x, where this is h sub x is delta h of x comma y by delta x. Similarly, r sub v is r sub y, which is 0, comma 1, comma h sub y. So now let us go back to Ru cross Rv, and this is just the determinant. Put I, j, k here, and this becomes 1, 0, hx, 0, 1, hy. So we have to calculate the determinant of that and take the modulus squared of that. That gives me g. Okay? So this becomes, first of all, I times minus h sub x minus j times h sub y plus k. These are all unit vectors. And this I need to take the modulus of. So mod of RU cross V is just mod of this particular quantity that I have here. So this is hx squared plus hy squared plus 1. Okay? So this is g squared, and g is just the square root of 1 plus hx squared plus hy squared. Okay? So now that we've also done that, we can also find what the normal to the surface is, because we've already done the work required to do that. The normal to the surface is just this particular vector here. Okay? So the normal to the surface n hat is z hat minus hx times x hat minus hy times y hat, where instead of I and j, I've used the hx, I've used the x hat and y hat terms.
Normal is just audio cross RV, right?
That's right, exactly. So that's a vector that we wrote. So without the mod here, it's a vector that we wrote out here. The only change in notation is that I've said I hat, j hat, k hat is, I've called I hat x hat, j hat y hat, k hat z hat. Just changing notation a little bit. But now I also have to normalize this. But I know how to normalize it because I've already calculated this object here. So this is divided by square root of 1 plus hx squared plus hy squared. So this is now the normal to the surface, and over there we have the metric of the surface, g. Okay? Now there's a little bit of algebra which I will skip here. I will just tell you what it is, what the idea is, and what we are trying to do. So what we wanted to do was to find out how curved the surface was. How do we do that? Well, one way to do it is to say, start here and go here. Let us suppose the normal points in this direction here and the normal points in this direction here. How much has the normal changed when we go between this point and this point? The technical way of defining what is called the normal curvature is to take the second derivative of r with respect to s. Okay? We wrote the first derivative of r with respect to s when we tried to write down this quantity here into ds squared. So how much r is changing as you move along a little line s. So for here we have to take the second derivative of r with respect to s. This is still a vector, and dot it with the normal. Okay? So this is a quantity that has a more complicated form. I will just write down what that form is, and I will not derive it for you. Because it's a dot product, it's a scalar. So this quantity is just L times du squared plus 2m times du dv plus n times dv squared, and it must be normalized by E times du squared plus twice s times du dv plus g times dv squared. This is what we calculated earlier. This is a new thing here. And here the definitions are L is n hat dot r u u, m is n hat dot r u v, and n is n hat dot r v v. So all you really need to know is to remember these definitions here for how you calculate L, m, and n, and these quantities here. These are all, we know how to calculate R, U, RV, etc. because we've done that earlier. we can now calculate the second derivative of r u u, r v v, etc. Put this all back in, calculate, you've already calculated the normal here. If you calculate this, this is by definition something called the normal curvature. Okay? Now, we are not going to do this in any more detail than this. This is just telling you what the definition is. But what I want to do is to give you a little more of an idea for what this means physically. Okay? So, the physical idea is that once I go to the tangent plane of the surface, so let me just sort of imagine a surface like that. Here, I imagine a point here. Let this point be at some distance, say z0 from this axis. And now I want to ask, when I say how curved it is, what I mean is as I move away from this, along this line or this line or this line, how fast does the surface move away from this flat plane? Okay? So, one way of saying that is to say, let z, which is the height of the surface, be z0, which is this height here, the z0, plus a factor that depends upon how far you move in x and y. So, let us just write it down first and then try and understand what it means in more explicit form. So, this is L divided by 2 u minus u0 squared plus n divided by 2 v minus v0 squared. Otherwise, I can also write this as z0 plus 1/2 of a ka x minus x0 squared plus 1/2 kb y minus y0 squared. There is some magic that has actually gone into this, and in general, as I move away from this point, the change in height of the surface is some combination of x and y. It's not just simple split up like this. But there's a general theorem that you can always find a basis of vectors, of directions in this plane, such that it splits up into a path that is purely along x and purely along y and doesn't mix these two paths up. Okay? So, these quantities Ka and Kb are called principal curvatures. So, this is the height as a function of how at a particular point how it changes or how fast it changes as I move away from that point. Okay? This is first of all an intuitive way of thinking about it. Remember that if I sort of had to draw a curve like this, or an even more sharply curved like this, or an even more sharply curved like this, the way I would think about how strongly curved it is to say, all right, let me look at this particular point here. Let me see how fast it changes as I move away from that point. The faster it changes, if suppose it was truly sharp here, I would say this is a very highly curved point here, because around this point, the direction, the height of the surface varies very sharply around the central point. Okay. That's essentially the idea that we want to formalize here. Except that in a surface is unlike a curve, which is something like this. Here is an x, here is a y. A surface has many directions. I can say, oh, what happened if I moved along this direction, or if I moved along this direction, or this direction? And the answer for each of those directions, there is some combination of factors saying delta u squared, delta v squared, delta uv. Okay? Along one particular set of directions, choice of directions, it's purely du squared plus d plus something times du squared plus something times dv squared. So, these are called the principal directions, and the coefficients here are called the principal curvatures. And these are the important points. Once I know these, then I know along any direction how does the height change. Okay? It's the same thing that you know that once I know the eigenvectors of a particular matrix, if that matrix is real symmetric, then I know they form a complete basis and I can expand any deviation in terms of that, in terms of those eigenvectors. I can expand any state in terms of those eigenvectors. The same sort of logic holds here. I haven't actually shown you this. This is more proof by conviction or something than actual demonstration. But that's because there is some amount of algebra that actually goes into proving these results, which is not necessary at this point for you. All we need to know is to have some intuition for how you describe a surface, what is the structure of that description, and the fact that it must involve two curvatures, because there are two directions, one in x direction, one in y direction, and there is some optimal choice of this such that it becomes completely diagonal in terms of deviations from that point here and here. That isn't all, because there are a few more definitions here. First of all, it turns out to be a little more inconvenient to work in terms of Ka and Kb themselves. What is often done is to work in terms of a quantity called H, which is 1/2 Ka plus Kb. This quantity is called the mean curvature. One second. The other quantity is called Kg, which is Ka into Kb, and this is called the Gaussian curvature. Yeah.
So we assume the surface in such a way that from that point the curvature in all directions is symmetric.
So the instruction is you go to a particular point, go to the tangent plane of that particular point, and then ask how does the surface behave if you move away from the tangent plane.
But if it is around a certain radius, if the curvature is different in each direction, then even if we choose our basis in such a way that we can do this principle,
It always works. It always works. So even if so these are the two special directions along which this becomes completely diagonal in the deviation delta x square and delta y square. So in general, as I move, suppose I have some surface here and I have some coordinate system here. In general, as I move away from this point, the surface is described by something which is du squared, dv squared, and du dv. It's a purely quadratic function of these quantities. But along some special directions, the du dv term vanishes if I choose my coordinates correctly, and only these two terms contribute. So it now becomes diagonal. Once I know what those diagonal elements are, I can change my coordinates to describe any other direction. So along any other direction is some combination of du square, dv square, and du dv, which I know explicitly. I can calculate it. But there is a special meaning to these extremal directions. So you might call them extremal directions. And once I know what the values of the curvature are along these extremal directions, I know what I can calculate it for any curve along the
Is this extremal directions the eigenvectors?
They are the eigenvectors. I haven't told you what eigenvectors of what, but they are eigenvectors of the principal curvature of the curvature matrix, as it turns out. Okay. So the mean curvature and the Gaussian curvature are important ways of thinking about the behavior of membranes. And let's sort of look at simple examples of what these are. Sometimes these are also written in terms of the radii of curvature. So remember that the the curvatures are the inverses of the radius of curvature. So I can also write this as 1/2, 1 over radius of curvature in the a direction, plus 1 over radius of curvature in the other direction, Rp. And this would be 1 over Ra times Rp. So this is in terms of radii of curvature. Okay. Having done this, we can now do some simple examples. First of all, suppose I have something that is really flat, completely flat. Okay? Then the radii of curvature are both infinity, which means 1 by infinity is 0. So the completely flat sheet has 0 mean curvature and 0 Gaussian curvature. The flat membrane has 0 mean and 0 Gaussian curvature. Suppose I have something that looks like this, like a cylinder. Okay? Then what can you guess are the radius? Suppose the cylinder has some radius r here. What is your guess for what that should be? Both the mean curvature and the Gaussian curvature are. So remember how to think about this.
One is infinite, one is r.
Yeah, correct, exactly. So one of the radius of curvatures is r and the other is infinite, which means that the Gaussian curvature is 0 and the mean curvature is 1 by 2r. What happens for a sphere? Okay. Here, the mean curvature is 1 by r plus 1 by r, which is 2 by r, goes with a factor of 2. So the mean curvature is 1 over r. And the Gaussian curvature is 1 by r squared. Okay, for a sphere. What about a structure that looks a little bit like this? I can never draw this right. Okay, so that it sort of bends down like that and bends up like that, about that point. What is the structure here? What does it look like?
I didn't understand this concept.
So this is something that looks like a saddle. If you've seen a horse and a saddle on a horse, where you sit, it's something that looks like this, which is when you face forward, and on where your legs are, it sort of bends downwards like that. So a saddle-shaped surface, can you guess? Let us say that this has radius r and this has radius r on both sides, just to be symmetric. Important point is that one curvature is positive, one curvature is negative, because it moves in the other direction. One curvature, the curve comes down in one direction, the curve goes up in the other direction. Okay? So that means that these two quantities are equal and opposite in sign. So this has zero mean curvature in this very simple specimen. So this has zero mean curvature because both have opposite signs if these two radii are the same. Whereas this has a negative Gaussian curvature. And this is called a saddle. Okay? Okay, let me just finish up with some words about how we use these ideas to think about the energetics of membranes. Okay? So, given a membrane, given, as I said, a parameterization in terms of u, v coordinates that tell me where a particular, given a u and v, where a particular point on the surface of that membrane lies, we calculated various things. First thing we said was the area of the membrane was the integral of du dv times square root of this quantity called g. And I pointed out that writing it in this form was very important It was important because this was a way of ensuring that whatever my choice of u and v, the answer for A would remain the same. One way of saying here is an amount of energy that I assign to the surface with a fixed area A is to say there is some energy which is sigma times A. So where sigma is an energy per unit area multiplied by an area, this is an energy for the surface. Okay. The more the surface is, the more the energy it has, let us say. But now we know another way of characterizing the surface, which is in terms of how much energy it costs to bend the surface. The surface can both change its area, but it can also bend without a significant change in its area. All right. And the energy associated with that, which is energy for bending, is just an integral over this area element dA. And the way it is normally written is as 1/2 times kappa times k squared plus kappa bar times kg. And here I go back to, okay, so let me just use a better notation here. I've used a slightly different notation from what I had earlier. I defined my mean curvature to be 1/2 Ka plus Kb. I can define a quantity which is really very much the same thing, which is called an intrinsic curvature, which is Ka plus Kb without the factor of 1/2. Okay. Now that simplifies things a little bit. So what enters here now is this quantity K, which is the extrinsic curvature. So now I have some bending modulus, and here I have another bending modulus, and this is the Kg, the Gaussian part of the curvature that I wrote down. Okay. This particular part here simplifies in Monge gauge to be integral dx dy del squared of h the whole squared. But this is just one particular simplification in one particular choice of what my u and v are. What we don't need to worry about it, strictly speaking. So all we need to know is here is a surface. I know if I tell you R of u and v, you know what the surface is. From the specification of R and v, you can calculate things like what is the metric and therefore find out what is the energy, total area of that surface. But you can also do interesting things like understand what is the curvature associated with every point on the surface. If you say there is some energy that I will associate with curving the surface, the answer is go to every point on the surface, find out what the curvature is. This kappa squared says it doesn't matter if it curves upward or it curves downward, it has the same energy. This quantity is what I must multiply that quantity with in order to get a dimensional quantity of energy on it. So it's the energy cost of creating a certain amount of curvature. These two terms are independent of each other. Remember we had Ra and Rb, or Ka and Kb, which we wrote in terms of this quantity of this particular combination K plus Kb by 2 and Ka Kb. So these two quantities are independent of each other, therefore what multiplies them is also independent. So now the energetics of the membrane comes from finding out what is the area of the membrane and therefore multiplying it by an energy per unit area, but it also comes from the cost of deforming the membrane, giving it curvature, and that is measured, the amount of energy you pay is measured by this and by this. The reason that this has been a little bit mathematical, but that mathematics is important, because it is not easy to define the problem in such a way that it is independent of your choice of coordinates. Whatever your choice of polar, something vague, they don't have to be orthogonal to each other. Whatever your choice of coordinates, the answer, provided you write it in terms of these quantities here, will remain the same. So as I said, these expressions are covariant with respect to or invariant with respect to the choice of coordinates. Once I do that, once I write those expressions, then I'm free to choose something that is particularly convenient to me. If I'm talking about more or less flat membranes, it's always convenient to use a Monge gauge. If I'm talking about a curved vesicle and asking about the energy it might be more useful to use sort of spherical coordinates. So it is dictated by what is the ease of a particular application. But the ability to go from one choice to another choice to another choice is made hugely simple by the fact that we can calculate invariants that remain the same irrespective of whatever choice you make.
So from where do you get these terms, as in are they available to us for a membrane?
Yes, given a particular membrane, this is a property of that material. This is how much energy it costs to make a particular bend in it. So the way you might measure it is to take a flat membrane here, curve that flat membrane so that it becomes part of some sphere, and find the energy that you need to go from here to here. So in this case, you know that this quantity is 0. The flat has 0 mean curvature. This has a curvature of say 1 over r. So the energy going from here to here is quantified by whatever term I put in here. Similarly, all of these quantities, I can take a bilayer membrane, I can pull at it a little bit, change its area and ask how much work did I do to do that. That work that I did is the increase in the energy of the system. So that's one thing that I can calculate. Similarly, I can each this and this I can also calculate. Okay. So let me just tell you one funny and surprising thing. The second term here, this integral dA of kappa bar kg, the integral of the Gaussian curvature, actually turns out to be independent of whatever you do with the shape, provided the topology remains the same. That is to say, let's suppose I said I'm going to calculate the Gaussian curvature. First of all, I'm going to calculate it for a sphere, which is sort of closed up logically. Then I'm going to take the sphere and I'm going to deform it in a complicated way that makes it look like this. The Gaussian curve, the integral of the Gaussian curvature is the same here and here and here. It's only if I have a surface for which I have to actually break material, so I make a little hole here, then the topology changes. It goes from the topology of a sphere to the topology of the donut. This has a different value for the integral of the Gaussian curvature. So that's very important observation, because it says now that we have done this problem, we don't even need to worry about this, provided you don't change the topology of the membrane. If you just look at a membrane that is fluctuating about its state and not actually driving holes inside it, you needn't worry about that term at all, because it remains the same. That integral remains the same irrespective of how I deform it, provided I introduce no holes into the system. So that's just an interesting mathematical observation that turns out to be important for mathematical reasons, but is offers you some level of simplification in this particular case. Okay?
So Monge gauge is this integral that we compute?
No, Monge gauge is a choice of u and v. So remember that what we need to do is to specify the vector from the origin to the point on the membrane as a function of two coordinates u and v. Okay? So now if I choose my u to be the x, v to be the y, then my vector r becomes x comma y comma the height of the function in the z direction h of x comma y. But in general I could have theta, this thing, and then the coordinate would be r as a function of theta and phi.
For what sort of membranes this area is not considered?
In general, it can always fluctuate, because the area is, roughly speaking, it's a function of what is the interaction between adjacent lipids and the bilayer. So these can always fluctuate depending upon how much energy you assign to that, what the value of sigma is.
Part, the kg part, in the integral the second term, right?
Yeah.
Kappa bar
Yeah.
kg. That integral is conserved when we deform this membrane. But what is the second case you mentioned? The other membrane, the fourth picture.
This one. So I'm saying that particular quantity changes if you have topology. If you have a donut, If you have something with a hole in it, like a vada, for example, if you calculate that integral for a configuration like this is some different number. If you calculate that integral for this, or this, it's the same number. Okay, that's the full thing. That's the integral of dA of this particular object here. That is a quantity that remains the same. The only way it changes if the topology changes. So provided you don't change the topology, you can forget about that term altogether because it's just a constant term. Okay, so now we've sort of, this field is mathematically a little more technical than other things that we have done. And the reason is that this comes in a field called differential geometry, where I have to think about lines and surfaces and the behavior of metrics and distances between them and so on. So this is an as simplified version as I could possibly come up with for this thing. Basically to sort of show you where these quantities, the bending modulus and the radii of the radius of curvature Ra and Rb come from, what they mean in practice, and how one might begin to think about them. But if you want to do this in a little more detail, you'll have to sort of spend more time thinking about this and figuring out the more mathematical parts of it. Okay. So I'll see you tomorrow, same time. From Wednesday onwards, Rahul will teach. I'm away for a week. Then after I come back, I will again try.